Okay, Chapter 9 you can see is going to be titled Exponential and Logarithmic Functions, is what it should say. We have probably heard of exponential, but really don't know much about them. And logarithms, probably not a chance. So as we work through this, we're definitely going to be finding some new things out. Now, our actual first section has the following learning goals. Students will be able to recognize properties of exponential functions, apply exponential growth models, and graph exponential functions. So now we need a definition. So by that, all of the exponentials we will be looking at will be in the form of y equals ab to the x. So if you haven't seen that before, let's put it in a color we can see. That's definitely where we're headed. Okay, y equals ab to the x. Now take a look at the restrictions where a cannot be 0. Because you can see if a was 0, it would wipe that whole thing out. 0 times anything, 0. B we're going to assume is a number greater than 0. Could be a fraction, but it has to be positive. So b has to be a positive number. But b cannot be cannot equal 1. So if b was 1, and we're talking about how things grow, take any number you want and multiply it by 1, that number is not growing. It's not getting bigger, and it's not getting smaller. So in any way you talk about or categorize growth, you got to remember there's two ways to grow. Staying the same is not an option. So growing, getting bigger, increasing the size of something, or decreasing, which would be getting smaller, reducing, those are all words we've used. Now, if our equations have to be in the form y equals ab to the x, we like to think of x as the independent variable. But take a look. X, this is the first time we've seen it, is up on top. It's raised to a power. Where previously we were looking at x and it was on the same line, we'll call it, as everything else. So now the unknown is up on top. Now, if that's the case, notice carefully, we're going to be calling b the growth factor. Now, I've already described b can grow in two ways. It can be a positive growth or an increase, and it can be a decay or a negative growth, a decrease. So think of it that way. Growth, truly in a positive vein, is increasing, and in a negative vein, it's decreasing or decaying. A will be the y-intercept. We also like to call it the initial value. So in a real-world problem, if I say, hey, the population was 30,000 people in the year 2000, what can we expect the population to be after a constant growth over time? What can we expect it to be maybe in the year 2015? The graphs of these exponentials are called exponential curves. There is no real nice name like, for example, a parabola. So every single squared equation had a graph of a parabola. We don't have that here. It's just an exponential curve, and you're going to see some differences, some similarities as we go through and graph a couple. So knowing that our first section is all about exponentials, the logarithms will be later. And this first section is actually about exponential growth. Okay? So anything that grows would be a positive b value. We consider it increasing. And then we're going to talk about that a and that b and to the x power. So let's move on and let's take one of these examples and let's write our equation up here again, our generic form that we're going to be looking for. Whoops, that's a little wide. Y equals ab to the x, keeping in mind what each of those represent. So when you look to the left and you see that first one, if I said, what's a? And you could say the initial value. You could also say the y-intercept, but basically we're asking for what's a? In this case, it's 5. What's b? 2. and your exponent is your unknown of x. In the second one, dark purple, we have an a value of 1. Good. It is not a 3 because notice in the equation, the generic equation, all of these are going to follow, the number that's raised to the exponent is the b value. The number in front of that is that initial value, that y-intercept, starting value, some of you would like to call it. All right? So on that one, 3 is the b value, 1 is the a value. And then the last one, light purple, we have a b value of 1/3. We have an a value of 2. So the big difference is, what does that b value mean? We said in this section, we're going to be talking about growth situations. So right now, if I said, which ones of these are growth and which ones are decay, you had better be talking about looking at the b values only. And so if I look at the b values on the first one, that b value is a 2. The b value on the second one, 3. The b value on the third and final one, 1/3. Which ones represent growth? The ones that have a b value greater than 1. So right now we know this situation is exponential, but it's not growth. Since our first section is about growth, we're going to graph one of the others. And let's take the y equals 3x, probably because that's just basic at this point. So if y equals 3x is our equation we're graphing, you get to pick powers. And again, we would pick positive, negative, and 0 values. So I'm going to put a few in. Don't need many to get a good look. And so probably doing positives first. So we'll start with the 2. If we said 3 to the second, putting a 2 in for x, we would get a y value of 9. 3 to the first, 3. 3 to the 0 power, we know anything to the 0 power is 1. 3 to the negative first, we know that means flip me, reciprocal, so we're thinking, that's the fraction 1/3. And then on the last but not least, if I put a negative 2 in for x, 3 to the negative second really means, again, flip me, I'm the reciprocal, 1/9. It does not mean I'm a negative number. So if we went over to our graph and assumed this was by ones, looks like we should be able to do this if it's by ones, we need to graph. Now, maybe I will make my pencil just a little smaller so we can get good spots here. All right, here we go. 2, over to the right 2, up 9, there's 5, 6, 7, 8, 9. Place your point. 1, 3. 0, 1, negative 1, positive 1/3. So just up a little, and then negative 2, 1/9. And that's even smaller than what we had before. And if we continue this process and I put a negative 3 in there for the exponent, a negative 4, a negative 5, we're not going to get negative numbers, we're just going to get smaller and smaller fractions. So this equation is getting closer and closer to 0. So we are going to run our line right along that x-axis, move it up, graph, sort of missed on that top point, but otherwise it was pretty good. Take a good look. We have what is called an exponential curve. We don't have a parabola. It snakes and hugs that x-axis over here on the left and eventually starts rising. Remember, we called that initial value or y-intercept, that number in front of the b. And on this case, remember, we could sit here and say a was really 1, b was 3, b represents the growth factor. So this time the thing is growing by a factor of 3 every time, every new value you put in. And that's exactly what shows up in the XY table, and that's exactly what shows up in our graph. Okay. So exponential curve, this is an exponential growth equation. With that, let's do a real world example and I think we'll be finished. The world population in the year 1985 was 4.9 billion people. At the growth rate of that time, the population would double every 35 years. So right there, they're telling you everything you need. But we're going to start off again with, remember, our equation needs to be y equals ab to the x. That's the form we're looking for. Now, part A. Write an exponential equation modeling this situation. Let x equal the number of 35-year periods. That's key. So x is our exponent, but remember, it's a 35-year period. Oh, so if I put in a 1 for x, that's 35 years have passed. I put in a 2, that's 70 years have passed. That's what you need to think of. And then let p equal the population. So if we go with what's going on here, the population we're trying to get would be p, so that's y. Our initial value, according to this, was 4.9 billion. You either remember that or write it in. You could write it out, but we want to remember it. And then our growth factor said it would double, and a doubling means a 2. Every 35 years, so there's our exponent to the power of x. Remembering x is a 35-year period. So 4.9, unless you wanted to write it out with all the zeros, billion times 2 to the power of x. That would be the exponential equation that models this. Now, there is a follow-up. You notice that was part A. So we're going to bring that equation back over here. So y equals 4.9 billion times 2 to the power of x, remembering x was every 35 years. So it says, with this model, what would be an estimate for the world's population in the year 2000? Now you have to remember that it started in 1985. Well, 1985, if you go back, just to show you, that's what it said. So there, in the year 1985. So in reference to 1985, what we're looking for now is the year 2000, and that's only a difference of 15 years. And they said this would be a 35-year period. With this model, what would be an estimate of the world's population in the year 2000? So right now you have a slight problem. Y equals 4.9 billion, and we'll put it in as billion, times 2 to the x has to be a 35-year period. And if we don't have it in 35-year periods, we're going to have to write it like a fraction of 15 over 35. Now start thinking, what does that reduce to? If I take a 5 out of both, that would be 3/7. So I suppose if you wanted to write it as 3/7, that would be another way to write it. You could. So grab your calculator. This is going to be a multiplication that you have to do. Now be careful in entering your 4.9 billion. Make sure you get enough zeros. 4, 9, 0, 0, 0, 0, 0, 0, 0, 0 times 2 to the power of, and make sure you put that 3/7 in parentheses, unless you have the calculator that moves it up. So right now, with this model, what would an estimate for the world's population in the year 2000 be? So we would estimate our population to be, and this gave us in actual numbers, so 65949110944. If we put our commas in where they belong, whoa, erase that last one. Only 2 digits. 3, 1, 2, 3. We're looking at approximately 6,594,910,944. All right. What was the population in 1980, assuming this growth factor? Oh, now 1980 goes backwards because we were at 1985. And so in that case, y equals a 4.9 billion again, 2 doubling to the x. And if we're going backwards in time, you should be using a negative value. And again, it's a 35-year period, so make sure you do that. Again, you could reduce that if you choose. And so if we know that our original population was 4.9 million, so let's go again, and you can just hit second entry to get back there if you want and change your equation. So all we need to change is that exponent, so we need a -5 divided by 35, or you could change that to negative 1/7, close the parenthesis. And we better be getting, yes, about, in 1980, we would have expected the population to be, put the commas in, 4,439,045,095. So you've seen a real-world problem with growth. You've seen how to set it up and what the characteristics of the graph look like. You should be good to go to try a couple growth problems. All right, any questions? Bring those to class.